Okay, I will talk a little bit about Frobenius method. So, say if we have a second order differential equations in the form of such x squared. Let's make a general case. Let's make x minus x naught square u double prime plus p x minus x naught u prime plus q x u equals to 0. So the way to solve this type of problem is just assume we have a series n equals from 0 to infinity, and we have our Fourier series will multiply another n to the r. So we substitute it, we wind up having something like that. Plus r minus 1 and plus r plus px and plus r plus qx a n x minus x naught. Oh, of course, sorry. For general case, it will be n minus x naught and plus r. Previously, it was just expanding around x equals 0. But for general case, we have that. So essentially, we just solve for the quadratic equation. Solve for that. So we'll have three scenarios. Of course, we know how to solve a quadratic equation. We have r equals to r1 plus r2. So we only have only one solution. Only one. Series exists. And r1 does not equal to r2, but r1 minus r2 is integer. Then we choose choose the larger one. As the only solution. you can check the smaller one as well to check if that is one of the valid solution for the equation. And the last scenario, R1 does not equal to R2, but they are not differ by integer. So they differ by, I don't know, 0.2 something is not an integer. So we have two solutions. So for this it only works for a regular singular point. I checked online. There's seems to have a really interesting way to solve an irregular point. As I talked about, the regular point is basically the increasing rate along the increasing rate along the singular point, something like that. The order of increasing is proportional to x to the r power. So it's like polynomial rate of increasing. So that type of singularity is regular singular point. We can solve it using a polynomial expansion. However, if I have a increase, for me, I need to find some color chalk. Okay. There's our polynomial increasing rate. Some polynomial. No matter how big it is, it cannot be bigger than, say, exponential. That is really like increasing really fast. What I mean by exponential is not x to the e, it's e to the 1 over x minus x naught. Something like that. So that's the purpose. So that there's a solution, there's a way to using this, like exponential of growth, which is way faster than the polynomial, to solve an irregular singular point. Basically, do the same trick. Assume y equals to exponential fx yx, where fx equals to ak x minus x naught k plus ak minus 1 x minus x naught k minus 1 dot a0, sorry, a1 x minus x naught, and y x is just like the solution to the regular singular point theory. A naught x minus x naught n plus s. So you substitute this into the differential equation and try to find all those coefficients. And apparently there is something to do with the order. So how much theory you need to take for f related to the rank of irregular point. So for the next few videos, I will give a few examples for different cases.